So let's get started. Welcome. Thank you all for coming, and it's certainly a pleasure to welcome Dr. Timothy Dolch. Him is in his fourth year as a postdoc at Cornell. Before that, he studied at both Caltech and Johns Hopkins. Caltech as an undergraduate, and Johns Hopkins as a graduate student. And as he'll tell you, he's heavily involved with the nanohertz gravity detection project, and we'll all learn a lot more about that from this talk. And Tim, small present for you for your say thank you for coming and giving us a talk. Thank you very much.
Well, thank you, Trent. And just wanted to thank everyone for having me, and Professor Rankin for all our hospitality and all the good conversation the last day. And we'll be looking at it tomorrow as well. So it's been an exciting time. And so I wanted to tell you about the whole effort of detecting gravitational waves with pulsars. And by the way, can everyone hear me all right? Okay. I'm going without a microphone, but if I have a gradual decrease in volume over time, you can let me know. I'm going to be telling you about pulsars in general, how you can use them to detect gravitational waves, and then finally a particular project that I've been working on, which was observing one pulsar for 24 hours straight. And I'll get to that toward the end. Before I go on, let me mention that much of what I'll be saying comes from a recent issue of the journal Classical and Quantum Gravity. And there was an entire set of papers, and many of the contributions were from the NANOGrav collaboration I'll be telling you about. And they form a venerable textbook about the status of the field right now. So if you want to learn more about this, I would direct you here. So, but starting with basics, what is a pulsar? Well, it's a very rapidly rotating neutron star. It's a collapsed remnant of a star that has experienced a supernova. And pulsars are typically about 10 kilometers in diameter, and a spoonful of material from a pulsar weighs about the weight of a mountain, or mass, I should say. I don't know how to be calling that a weight, what kind of scale you would be using. But because of a misalignment between the rotation axis, which is here, and the magnetic axis, you get this, you get beamed radio emission, and because it's rotating, we receive the signals like a lighthouse beam. And so when they were first discovered in 1967 by Jocelyn Bell, people wondered very briefly, is this an extraterrestrial intelligence, because it was so regular. But for a lot of reasons, it fit the neutron star model perfectly. So when we observe a pulsar, we use a radio telescope, and we have a process of online folding, and I'll talk about that later. But what that means is that because we receive many pulses, the slowest ones tend to rotate at about once per second, and others up to 1,000 times per second. So we get a lot of pulses, we average those, and then we measure those average pulses with respect to a reference time, which is usually an atomic clock. So these are concepts that I'll be coming back to. Now, if you've taken an introductory astronomy course, you know that the fundamental stellar evolution plot that you look at is the Hertzsprung-Russell diagram, where you have color and magnitude. The correspondingly important plot for pulsars is this, which is the P dot diagram. So P is the pulsar period, the rotation period, and P dot is the derivative of that period. And when you plot all the known pulsars on this diagram, you see that they cluster into two populations. One of them is the so-called canonical or regular, you can also sometimes called slow pulsars that rotate about once per second. And then the millisecond pulsars, which are around up to 1,000 pulses a second. And it turns out that there are very different stories behind a pulsar where it lies on this diagram. There's a whole evolutionary history. They tend to be born here and they move down here as they gradually accrete material from a companion object, and that speeds up their angular momentum with time. So whatever kind of pulsar you're observing, you receive pulses. But it's not that simple because there's a lot of things you have to do to receive the pulses with the regularity you would like. For example, there will be delays in time just due to the Earth's position. If you observe the same pulsar over a year, you get the delay due to that extra light travel time, for example. And there are many things you have to correct for with respect to our solar system. So you need a good solar system ephemerides, and that's all the information about the positions of the planets and everything to determine exactly what the corrected arrival times would be due to all those effects. So that's one thing you do when you're observing a pulsar. Now, when you've done all of that, if everything's perfect, then your timing residuals, and those would be the pulse arrival times with respect to that atomic clock, would be nice and flat. But if you haven't done everything perfectly, you get some sort of error here. So if you're, for example, if you're measuring the period of the pulsar incorrectly, and this folding process is when you're averaging pulses according to this known period, you get a slope in your arrival residuals. If you get the derivative of the period wrong, you get a parabolic error in your residuals. If there's a proper motion error, that's another thing you correct for, the actual motion of the pulsar in the sky, you get by the way, notice this is 10 years here, every year, due to both parallax and this increasing divergence from what we thought the position was, you get a sort of ringing effect here that's increasing the amplitude. And then if parallax is wrong, you just get the sinusoidal feature alone. And then there are things that are even harder to model, such as spin noise, and that's the intrinsic pulse emission time change. So even though it's very regular, and I'll show you in a minute just how regular it can be, there are tiny little diversions from that regularity that show up as this wandering in your times of arrival with respect to the atomic clock. But this has been done for a while, and many of these processes are very well understood. So when you correct for all of them, you get these nice flat residuals, and that means that your times of arrival pulses really match up to your model perfectly. So notice this is 5 years, and that means that our times of arrival are diverging only by 4 microseconds. And here, and this is one pulsar, this is another pulsar. Each of these have 2 different frequencies. And here you can see in many of the cases, it's only diverting from the model by about 0.2 microseconds, and that's over 5 years. So that shows you how well you can time pulsar. But let me say more about this folding process, because I've used that a bit loosely so far. The way it works is that so individual pulses are quite noisy, but when you start averaging them, a very clear shape emerges. And that's why you can use pulsars to measure some of the astrophysical properties, or you can use your times of arrival to measure some astrophysical properties at the pulsar very accurately. So because you have so many, for example, in 1 year you can have up to 10 billion pulses received, and you keep averaging them and averaging them, and the signal noise increases, and you can determine the period to about 14 significant digits, for example. And the same with the eccentricity of the orbit, and that orbit, I use the term orbit because many millisecond pulsars especially are in binary systems. They'll have a companion, often white dwarf or neutron star with them, and that's another parameter you have to measure. But it makes for some very, very accurate physical measurements. Now, when you're determining this time of arrival, you do it with respect to a template pulse. So the blue, this is to illustrate what I was saying about that single pulses are often very noisy. So these blue points here represent a single or maybe just very slightly average set of pulses. The red is the template pulse, and that's been averaged from maybe even years of observing. And you determine the time of arrival, the residual, and thus and one particular number of time of arrival, depending on how that template matches up to the individual single pulse. So here you can see we've matched it up well. Here, if you use the wrong template, for example, you get a residual that's pretty ugly. And that shows you the importance of having to use the correct template. And they change at different frequencies. So if you're measuring a pulsar at one frequency, you can't use that template to measure the times of arrival at another frequency. And this is a pulsar called J7D13 plus 0747, which is a very regularly pulsing millisecond pulsar. And you can see at different frequencies here. This is low rating frequencies going to high rating frequencies. The shape changes quite a bit. So that's something you have to be careful about, and that's something I'll be coming back to. And by the way, if there's questions at any time, just shout them out. Are there any so far?
What is the solid angle beam width of a pulsar?
It can vary quite a bit. But the estimates of those, there are distributions of those that are used to model the total number of pulsars in the galaxy, because you can estimate how many that you miss based on those angles. And so the total population is something like 80,000 in the galaxy. But it can vary quite a bit as needs. So if you've done all of that, like I said, you should get what's called white noise residuals, meaning just featureless, flat, uncorrelated noise. And that's good. Except even in that noise, there's information. So part of that noise is merely due to what's called radiometer noise, which is just the inherent noise in your instrument, in the receiver, backgrounds, and so on. Local backgrounds, that is, and then you also have astrophysical backgrounds. There's also pulse phase jitter, which is this wandering of individual pulses. So they converge to a nice average, but individual pulses can wander a bit, and that creates some white noise as well in time residuals. And finally, and this is kind of an abstract plot here, but it's showing the radio frequency spectrum with respect to time. And you can see that interstellar scintillation, or actually scattering and scintillation are occurring. And that's because there's an interference pattern. You have all the pulses that pass through the interstellar medium and then converge again. And just like any interference pattern, you see this splotchiness, and that means that you get better signals some at some frequencies better than others. So that ends up being a white noise process as well in your time residuals. So there's some astrophysics in there as well, even if you've corrected for everything else. But what gets ugly is that if you're timing a pulsar for 10 years or more, you start seeing what are called red noise residuals. And that term comes from signal processing. It's called red noise simply because it means that there's more power in the larger scales, so red and long wavelength. But other than that, it's just kind of a cute term. But if you time a pulsar for 10 years and you fit out everything correctly, all those things I was talking about, the solar system effects, and you have it at the right frequency and everything, you can still have this wandering. And what can that be due to? Well, like I was saying in that plot before, it can be due to intrinsic spin noise. So it's something that's happening at the pulsar that there's really nothing you can do about. It can also happen because the intervening interstellar medium also creates this wandering in your time residuals. And that's called DM variations. DM means dispersion measure. And there can be a red signal, which could be gravitational waves. So if there's something left over that has this 10-year period or so, 1 to 10-year period, 1 to 10 years, if you broke this waveform up into components, it will look something like this. But you have to be careful to separate out these other kinds of noise first, and that's what I'll be talking about. So now that we're on gravitational waves, let me first mention that the first indirect detection of gravitational waves also occurred through pulsars, through a totally different method than what I'll be talking about. But this is the Hulse-Taylor binary, and it was a pulsar with another neutron star non-pulsating companion. And you can measure the period of that system over time using the times of arrival. And this was done in our beloved Arecibo telescope in Puerto Rico, which remains the finest instrument in the world for studying pulsars because of its huge collecting area. And some of you in this audience have been there recently. If you track the period of that system over time, it decays in this perfect way. And I say perfect because it matches up exactly with what general relativity predicts if the system were emitting gravitational waves. So the correspondence was so perfect that Hulse and Taylor got the Nobel Prize in 1993, I think. And this represents the energy loss if the system were emitting gravitational waves. But it's still an indirect detection because you don't see the wave directly. You just see the energy loss if the waves are being emitted. So what do the waves themselves actually look like? Well, this shows a coalescing system. In this case, it's two supermassive black holes, but it's the same sort of picture if you're looking at two neutron stars that are merging toward each other. It's a prediction of Einstein's general relativity, such that if you have a quadrupolar moment, such that there's no spherical symmetry. So, in other words, a single black hole or single neutron star won't be emitting gravitational waves, but a pair of them coalescing because the system as a whole has the spherical asymmetry. It's predicted to emit a lot of gravitational waves if it's massive enough. And we measured the effective gravitational wave by strain, this is h, and that's essentially the degree to which space is stretched out. So if a gravitational wave passed this room, in principle you would see the room stretch out and differentially. And so if it was just in one direction, the ruler would stretch along with you and you wouldn't notice anything. But what happens is that it stretches in this way in an expansion, and in the perpendicular direction in a contraction. So it's that difference where you would measure the gravitational wave passing.
But,
Please.
But you've got a ruler that's stretching along with it, right?
Yes.
So how do you see it?
Next slide. But let me also say, before I need to be worried, that the gravitational wave strain tends to be, as far as our experience is concerned, on a smaller scale than the nucleus of an atom, so we won't actually see that happen. Actually, 2 slides from now, but it's coming. So if you had two coalescing supermassive black holes, what would that whole process look like? Well, it might spend about 1 million years in this regime where the objects are orbiting each other with a period of about 1 to 10 years. But that period is gradually increasing and they're getting closer together as the system is emitting gravitational waves, in the same way that that Hulse-Taylor binary was. As they approach each other, both the amplitude of the emitted gravitational waves and the frequency increases, and this is called a chirp waveform because if you play that, the sound goes whip like that. And finally, when they merge, there's this other mysterious thing that happens called a burst of memory. And what that is a step function waveform. So in addition to this chirp sound, you have just a sudden jump. And that has to do, it's a very deep thing in general relativity, but it has to do with the fact that space-time itself remembers that a merger occurred there. So it's another kind of waveform that can be detected. And what's not shown on here is that if you go out in another 1 million years or so, it jumps back down. And this is a very solid prediction of general relativity as well. Okay, but how do you detect gravitational waves? That was the question. And the most well-known way to do that is with laser interferometry. LIGO stands for laser Interferometric Gravitational Wave Observatory. The primary facility was in the desert in Hanford, Washington State. There's another one in Louisiana, there's one in Italy, there's a number of them around the world. But this is essentially the same setup as the Michelson-Morley experiment, where you have a series of perpendicular paths for light beam travel. So there's a very well-tuned laser that goes down toward one end and back, and then you recombine them and look for a phase difference. And that subtle phase difference can tell you if the length of one of these arms has changed with respect to the other arm. And so it's a differential thing. In one direction you couldn't do it, but when you recombine those phase changes in the laser beam, you can see if tiny differential changes occur. And the strains that LIGO is aiming to detect are on the order of 10 to the negative 21. So it's 1 part 10 to the 21 of a change of length. And like I said, that's less than the nucleus of an atom scale. So it turns out that so LIGO is over here in this diagram. This diagram is showing the sensitivity of pulsar timing arrays to different gravitational wave sources. So this is the frequency of the gravitational wave. And up here, so this is hundreds of hertz. So that the gravitational waves that LIGO would be sensitive to would have an amplitude, like I said, of less than the nucleus of an atom, but the oscillation frequency would be a couple hundred times a second, a couple hundred hertz. So these are high frequency but low strain. It turns out that gravitational waves due to supermassive black holes will also produce gravitational waves that are low frequency but high strain. So these could have periods of 1 to 10 years per oscillation. So maybe 10 years for once back and forth. But the bright side of it is that you have a very large strain, and this is where pulsars come in. But while I'm on the subject of gravitational wave sources, so I was talking about supermassive black holes, and that's largely what is residing here in gray. So these are sources that produce waves around 10 to the negative 15 strain and 10 years or so. There are also gravitational waves from the very early universe, and you might have heard about this in the news recently. And these are due to these are called relic gravitational waves, and they're from the era of inflation. So this is another whole method of gravitational wave detection. And it was gravitational wave detection along with very good evidence of the theory of inflation, which was proposed by Guth and Lind and others in the early 80s to explain a lot of different cosmological conundrums. But one of them is the strange fact that when you look at the cosmic microwave background, it's surprisingly uniform, right? If you look in one direction in the sky, you have this 3 Kelvin or so microwave brightness, and in the other direction of the sky, it's the same. And so you're looking toward the early universe in either direction from which this microwave background emission emerged. But how does that one side of the universe know that the other side of the universe was at the same temperature? And this is where the theory of inflation came in, is that very, very early in the universe, we're talking like 10 to the negative 30 seconds, there was a very rapid expansion of the universe before the ordinary Big Bang as we know it kicked in. But in that period, it turns out, for various reasons, there were a lot of gravitational waves in it. So one of the predictions from the theory of inflation was that in the polarization of the microwave background, you would see these blotches. And that would be evidence, on the one hand, of gravitational waves having occurred and the fact of inflation having occurred. And this was what was probably seen by the BISEC-2 experiment, and that's an microwave observatory in Antarctica, just about a month ago now. and it's a really big discovery. It's being verified, but it's really good news for all of gravitational wave science, because the scary thing is there's a lot of energy being invested in gravitational waves, and yet the only detection so far was an indirect method. So this is, it depends on whether you want to call it direct or indirect, but either way, it's really awesome that there's another level of discovery of gravitational waves that's really pushing the field forward. This is see these maps in more detail. This is the actual gravitational wave structure from the era of inflation that today affects the polarization of the microwave background. Here's some more plots from their papers, but basically they just show that here's some of the previous measurements, and this is a power spectrum of those fluctuations. So in the previous plot, you see these blobs due to the gravitational waves in the early universe, and here, if you take a two-dimensional power spectrum, you see this, which matches the predictions of red here perfectly. But let me put those in context with everything I've said so far. This diagram closely corresponds to this diagram. Okay, so we have period, or rather frequency, and strain of gravitational waves. So we have the same axes here. And so, like I was saying, LIGO and other ground-based detectors are looking for these high-frequency, low-strain gravitational waves. Pulsars, longer periods, but stronger strains. By the way, in between, there was a canceled space mission that was going to do this in orbit to get the in-between realm, and it was canceled in NASA's 2010 budget. So, write your congressman about that. But the gravitational waves probed by BISEC2, by inflation, are here. So in the Earth universe, for gravitational wave, it's a very high strain, 1 part in 10 to the 5. But they're also extremely low frequency. But those blobs I was showing you in the previous slide are gravitational waves. It's these extremely long frequency gravitational waves. But back to pulsars. So how do you detect gravitational waves directly with pulsars? Well, you imagine a pulse train coming toward Earth from a particular pulsar. And I was telling you about the rulers before as sort of an analogy for what happens to the gravitational wave. There's a differential stretching. And the differential part we'll get to, but you have to you need at least one ruler to do that. You have to, in principle, have that ruler stretch. Well, if you think about the distance between pulses, that actually sets up a very nice ruler. In fact, this looks a lot like a ruler. It's got very regular tick marks because we have very regular pulses. So if there is a gravitational wave passing, you might notice those pulses stretch further apart. And that would correspond to a longer period between pulses in a particular pulsar. And in the long term, if you have, for example, a change between pulses that corresponds to 100 nanoseconds, and that happens over 10 years, it's a simple ratio to get to the gravitational wave strain, which is 1 part in 10 to the negative 15, and that's where that placement on that diagram I was showing you comes from. So that's the sort of strains we can detect using this method. This diagram, I apologize, is a bit busy. But just like I was showing you before, if you have something unmodeled in your timing residuals, you will see that as a divergence from a straight line in your time of arrival residual plot. A particular gravitational wave source, such as one pair of gravitational wave of supermassive black holes merging together. So say the period of that was about 2 years of that system. Well, the timing residuals in a particular pulsar will look something like this, because you had that unmodeled effect on your pulsar arrival times. That would be from an individual supermassive black hole binary. But there are other types of gravitational waves you could also detect. The memory, those mysterious things I was telling you about called memory bursts, where there's just a sudden jump, it's a step function wave, right at the time of merger. That would affect your timing data by a simple change in period. The period would suddenly get larger or smaller depending on which jump you're talking about, and your timing residuals will look like this. And this is another picture of that memory burst waveform. But more likely, well, I shouldn't say more likely because we don't know yet, but if you had that, the most likely source you would see is what's called a stochastic background of gravitational waves. And what that means is that you have all of the merging pairs of supermassive black holes out to about a redshift of 1.5. So this is a huge volume of the universe. And individually, they're too faint to detect in a way like this. But they all sum together incoherently to make this gravitational wave background. So such that if you broke this residual up into its Fourier components, you would see periods on the order of 1 to 5 years with a certain spectrum to them. But individually, you couldn't see the source. But this stochastic background is probably the strongest source that you could see with pulsar timing. And that's what I'll be coming back to quite a bit. Okay, so I talked about NANOGrav. I never defined it. It's the North American Nanohertz Observatory for Gravitational Waves, and it's a collaboration of astronomers, and it's interesting because it's come together both from its members such as Professor Rankin, who are coming at it from the pulsar side, and a lot of people who are also coming at it from the purely gravitational wave side, who just study general relativity and are predicting the sort of sources we see. And then there's also the International Pulsar Timing Array, of which our North American collaboration, US and Canada, is one component, but there are similar collaborations in Australia and in Europe. Here's the organization of it. In case anyone bureaucratic is watching, we're very organized, but I won't waste any more time on that slide. So suppose that you detected some sort of gravitational wave-like residual at your time. How would you really convince yourself? Especially if it's a stochastic background looking like this. You know, how do you really tell that apart from one of the other processes I was talking about, such as intrinsic spin noise or something like that? Well, there's two kind of smoking guns about it. First of all, the whole thing about gravitational waves is that they are quadrupolar. So like I said, you have this expansion in one direction that's simultaneous with a contraction in another direction. And the way, so what that means is that you have to monitor multiple pulsars. One pulsar alone cannot detect gravitational waves. You might put limits on it by saying that, you know, if we see nothing oscillatory at all left over, then there's no gravitational wave, but that's all you can do. But if you want to really prove to yourself you're detecting gravitational wave, you have to look at pulsars in many different directions over the sky and correlate them together. And that's how you can get evidence of this quadrupolar nature, which is one of the smoking guns. It's a famous paper in 1983, Hellings and Downs, where they showed that if you take, so this angle here is the angle between a particular pair of pulsars. And then we take how correlated those residuals are. If it's a gravitational wave background, the sort of correlation you would get looks like this. Whereas if the red noise like wandering were just something along a particular line of sight, then they would be totally uncorrelated. So if the waveform were due to something intrinsic to the pulsar, you would see a flat line. So this correlation is really one of the smoking guns. One of the other smoking guns is that gravitational wave strings are achromatic. So that means that the same level of period increase and decrease occurs at all radio frequencies. So it doesn't know anything about radio frequency. Whereas if your red noise process is due to the interstellar medium, for example, and this is this DM I was telling you about, which represents how much interstellar medium you're looking through, and that can cause quite a wander in your timing signal. But see, that's frequency dependent. So it happens more in a correlated way at higher radio frequencies than at lower radio frequencies. Actually, I'm sorry, it happens more at lower radio frequencies. The same can also happen with interstellar scattering. So this EM is just a total delay due to the line of sight integration with the interstellar medium. Scattering is about the spreading and then reconverging wave paths, or rays, I should say. And so you can also get a wander in your residuals due to scattering. But all of those things are frequency dependent. That's the good news. And so that's how you can model those. Now, the top of these panels here is that Helling's imbalance correlation curve that was shown. And the name of the game in this business is to time pulsars all over the sky for 10 years or more and start doing this correlation between pairs. And some of the pairs, so that means that the more pulsars you have, the better of a match to this diagram you can get. Now currently, we have, so NANOGrav uses the Arecibo Observatory that I showed you earlier and the Green Bank Telescope in West Virginia. This is the number of pulsars we monitor regularly at Arecibo. These are the pulsars from the Green Bank Telescope and the combined populations here. But there are new pulsars being discovered all the time. And so by 2020, here's the extrapolated number of pulsars we're monitoring. And you can imagine that this number of pulsars per correlation bin here will really fill up this diagram and lead to possibly detection. But having done all that, are there any astrophysical conclusions so far? And the answer is yes. Now, I apologize because this is kind of an abstract diagram here. But this is from a recent paper, Parkes Pulsar Timing Array. This is a radio telescope in Australia that's doing a lot of this work. And this is a measure of the strength of a gravitational wave background as an omega gravitational wave. Omega in cosmology tends to refer to an energy density, so there could be an omega due to dark energy, dark matter. So this is saying over the whole cosmological volume of the universe, if there's this gravitational wave, this stochastic background that's shooting around, how much total energy density of the universe is there? So that's what this is measuring. So the more that you move to the right on this diagram, the stronger gravitational wave background there is. So if you go back to this diagram, a weaker gravitational wave background would move down on this diagram. So moving down in terms of gravitational wave strain here corresponds to moving to the left on this diagram. Okay. Now, this Parkes Pulsar Timing Array released a limit paper. So this is when you say, okay, we've done all these analyses, and we don't see evidence of gravitational waves yet, but that means that that's still meaningful information, because that tells you that whatever gravitational wave stochastic background is there has to be weaker than what you've already measured, and so that's why it's a limit. And the interesting astrophysics that comes out of this is that the strength of a particular gravitational wave background correlates to a certain model of galaxy evolution. Because, and this is one of the really interesting aspects that brings together many different parts of astronomy. So there's another whole field in astronomy of people who model galaxy evolution over cosmic time. So you can do a very elaborate computer simulation of millions of galaxies in a test volume, and you can see them coalesce, the galaxies merge with each other, they form more structure over time. And you can do this from very early in the universe's history until now. And it turns out that if you have two galaxies that merge, eventually their supermassive black holes will also coalesce together and merge. Because every gap, for the most part, for significantly large galaxies, there's always a supermassive black hole at the center of this galaxy. So if you have two large galaxies that merge, their supermassive black holes in the center will also, sometime after that, coalesce together. So that means that a particular history of galaxies and how they merged over billions of years will correspond to the number of supermassive black holes that have merged over billions of years. And that in turn will give you a certain strength of the gravitational wave background. So what these curves here are different models of galaxy evolution, and the gravitational wave backgrounds those models should produce. And there's a whole range of them. But this pink region here, this is the region of gravitational wave background that's already been ruled out. That shows you that this particular model, and it's called merger-driven model here, but it's a model that had a lot of mergers late in cosmic time. So that would have been a particularly strong background because relatively near to us, there would have been a lot of merging sources, and then we would therefore be stronger. That model has been largely ruled out already just by the non-detection of gravitational wave background. And that means that theorists can go back and modify the galaxy evolution models based on this. So there's already some interesting astrophysics coming out. So that's stochastic backgrounds. I also was telling you about continuous wave models, and that's just saying if there is an individual source that happens to be strong enough and near enough to us that we can see one sine wave from it, do we detect those? The answer is not yet, but we're approaching the ability to be able to detect those. This curve, this again here is the familiar frequency and strain diagram. These curves up here represent detection limits. So that means that nothing has, so below here we can't detect yet, and above these lines we haven't detected anything yet. But you can see we're about an order of magnitude away, and as we do this experiment for longer and longer, we monitor the pulsars for longer and longer, these curves will move further and further down. We eventually get to the regime where you get these green dots, which are some projected individual sources. So if you keep doing that over time, you might start to see, in a particular direction, individual merging source. And this diagram shows you that given all the pulsars in the sky that NANOGrav is monitoring, it has a sensitivity in a particular direction here. So we get some directional information out of this. So you're measuring pulsars that are all over the place, but the correlation between them becomes sort of an arrow saying, okay, here is a supermassive black hole binary that's emerging. IPTA has pulsars all over the sky. There are over 50 of them now being monitored on a bi-weekly basis. This has been going on for 10 years or more. I'm going to skip a few of these in terms of time. But I want to get to my list of reasons for optimism about the whole pulsar timing array. This diagram is showing how instrumentation has really improved with time. So the RMSTOA, that just means the uncertainty on your time residuals, and you want that number to be smaller and smaller. The smaller that number is, the more accurate of a clock you have. And you can see in the last 20, 25 years, it's just dramatically improved, by order of magnitude. And that's probably going to keep improving. So that's been a continual improvement. Here's an example. For 2005, 2012 at Arecibo, this particular pulsar was monitored. You can see, okay, these timing residuals are pretty accurate. But then when this new instrumentation called PPTA, which stands for Puerto Rican Ultimate Pulsar Processing when that was installed, look how dramatically these time residuals improve. So those sort of instrumentation improvements are happening all the time. Here's some more examples. The same, also increasing in bandwidth greatly improves the signal noise, pure and received pulses. Second reason for optimism is that with time, more and more pulsars are being discovered. That is absolutely crucial because, like I was saying, the real holy grail here is to populate that helix and Downs diagram, and so the more pulsar pairs that you have, the better. So adding more discovering new millisecond pulsars and beginning to time them and doing that for years and years is always going to help. And it's not just the faint ones that are being discovered now, there's even still a lot of bright millisecond pulsars that are being discovered. And you can see with time, the number is just dramatically increased. So pulsar searching for new pulsars is a huge part of this effort. And another reason to be optimistic is that these discoveries are not only happening in the radio frequencies. The Fermi Gamma Ray Observatory also discovers quite a few new millisecond pulsars, and it actually times them in gamma rays, just like we time them in radio. And many of these gamma ray pulsars turn out to be good radio timers as well. So we've got a number of pulsars added just because of this. And this was a pretty serendipitous discovery. This wasn't really planned. It was, and these sort of exciting things happen all the time. And so it's really benefited the pulsar timing array effort. And in an era where the Arecibo telescope and the Green Bank telescope are a bit under threat in terms of their funding, I wanted to mention that quite a few of these millisecond pulsar discoveries are happening with the GBT and Arecibo. So Arecibo is in red, Green Bank is in green. And it's a pretty essential part of that effort. I'll skip a few of these. So lastly, I wanted to mention this, another part of the NANOGrav effort that I've been involved with, called the 24-hour global campaign on J1713, this really accurate pulsar. So what we did is we used 9 telescopes around the world that included Green Bank in West Virginia and Arecibo in Puerto Rico and 7 others to monitor this pulsar for 24 hours straight. So as the Earth rotates, we would switch from telescope to telescope. That's why we need 9 of them. So we had timing residuals for 24 hours straight. And a number of observing modes were used. But the total data set ended up being about 70 terabytes, I think. This is how the spectrum of the pulsar changed over time. You can see there's all kinds of funny things happening in the interstellar medium. At the very beginning, I was telling you about how you need to use the right tablet at the right frequency because the pulse shape changes the frequency. You can see there's some dramatic changes in the pulse shape of the frequency. This is a representative pulse for all frequencies, but this is the difference each 50 megahertz frequency bin from that shape over 800 megahertz. You can see there's this huge change in the pulse shape of the frequency. This diagram is showing how the typical timing uncertainties improve with the number of pulses. So, if I take 10 minutes of pulses and I average all those together to get one pulse shape, how does the signal to noise of that shape and thus the time residuals improve with time? And for the most part, it's a well-behaved process because it improves with 1 over square root of n, where n is the number of pulses, because we're just doing averaging. But there's some interesting diversions from that law, and that's something that Professor Rankin and I were talking about a lot today, and something we're going to be working on. That's a great research interest of hers as well. So that's another part of this project. If you look at the pulse shape of all 9 telescopes, there's all these subtle features that come out. So this dark line here is the main pulse shape. But if you blow up this line by 50 times, you see all these tiny features here that they're on the bold line very faintly, but you can't see them until you blow them up. So there's all these other features going on here that have to do with the physics going on the surface of the pulsar. Finally, when you take time residuals from all 9 telescopes, and so this is the signal noise of an individual pulsar, or not an individual pulsar, an individual residual, so one 122nd chunk that's averaged together. And you look at the spread of those time residuals, it turns out that you have in order to model that correctly, you need to explicitly include pulse phase jitter, and that's that component I was telling you about, where individual pulses jump around. And this has been known about in this pulsar, but we haven't seen it quite in this dramatic of a fashion until this observation. And it's something to think about because it's an intrinsic limit to pulsar timing. You can't go to the pulsar and stop it from moving around. You have to live with that. You have to live with the fact that individual pulses being emitted from the surface of the pulsar are not going to be absolutely regular. So the timing we need to detect gravitational waves has to take that into account. And this is one way of understanding that better. And like I was saying, there's quite a bit of signal pulse data from this 24-hour experiment. And this particular analysis here is on a different pulsar, but it's one of the things we're working on this 24-hour project, where this is a mathematical method called principal component analysis. I won't go into it about to end, but you can use it to search for giant pulses that happen off the main pulse. And that's something that's also very important to understand if your timing is going to be accurate enough to look at gravitational waves. So let me just conclude there and remind you that NANOGrav and the Pulsar Timing Array effort in general is searching for gravitational waves in a complementary fashion to laser interferometry and also to the microwave background inflationary effort, gravitational wave discovery effort. And there's already some astrophysical implications of gravitational wave studies just by the galaxy evolution models that you can eliminate based on non-detection. And finally, we have this new 24-hour data set that's helping us to understand what subtle sources of noise are going on and then understand overall how those affect gravitational wave effort. So, thank you.
If you were to detect a signal in excess of your noise limits, it would tell you that gravitational waves exist. But we already know that from other evidence. So my question is, would you be able to tell something more about the signal, such as the polarization of a gravitational wave, or the pulse shape of a gravitational wave, or
yes,
other parameters of astrophysical interest?
Yes, absolutely. So the question was, you discover gravitational waves, but what do you do after that, essentially, right? And there's a lot, and in this talk, I didn't really get a chance to go into that, but of course, discovery would be a big deal. But after that, it depends on the type of source you're looking at. If it's a stochastic background, that itself is a measurement of galaxy evolution over cosmic time. And there's no real direct way to get at the number of galaxy mergers for cosmic volume over cosmic time. And that's something that people from the galaxy side, people who do Hubble deep fields, things like that, are really interested in. So that's the gravitational, that's the background side. For individual sources, there's also an effort underway to, and should an individual source be identified in a particular direction. People are preparing to observe it in other wavelengths. So there's a whole series of papers in that the journal I showed in the second slide that's about how to observe electromagnetic counterparts to an individual source. And so there's a sort of buzzword for this, which is called multi-messenger astronomy, meaning that if you have these exotic sources such as binary black holes that are emerging, can you see them simultaneously in optical, X-ray, as well as gravitational wave, and then you learn a whole lot about seeing those things happening simultaneously. As far as the actual waveforms are concerned, there's also a whole literature now about can you measure modifications to general relativity based on that. So if there are some theories of gravity that go beyond GR, that amount to slight modifications to general relativity, you might see some of those theories manifest themselves as unusual polarizations in the gravitational waves themselves. So there's a whole literature now on how to use some of these detected waveforms as a probe of those new physics.
When you spend 10 years looking at a pulsar, what fraction of the time are you actually looking at the pulsar?
So typically, for an individual pulsar, we observe it bi-weekly for a half hour, 20 minutes or a half hour. Some of the better pulsars we observe more than that even. But that's happening for 42 pulsars or longer regularly. So it ends up to amounting to a large amount of telescope time. But for an individual pulsar, it's 20 minutes bi-weekly.
So if you discovered twice as many pulsars, you would just have to cut, like, are you at capacity for how much telescope time you have to observe pulsars?
So over time, we've needed more and more telescope time. So far, we've got. So, hope that continues.